Hi, my name is Marilena Parker, and today we're going to be talking about the Hardy-Weinberg equation. We're going to split this up into 6 parts. 1. What is the equation? 2. Conditions for Hardy-Weinberg equilibrium. 3. What does the equation show? 4. The equation itself. 5. How to use the equation. And finally, putting it all together.
First, we will be discussing what exactly is the Hardy-Weinberg equation. Scientifically, it means the allele of genotypic frequencies in a population will remain constant from generation to generation in the absence of evolution. Essentially, if evolution is not acting on a population, its genetic frequency will stay the same. In other words, the population is not evolving.
Okay, so there are 5 conditions that must be met in order for this concept of equilibrium. So 1 is that there is no mutation, and then 2 is that random mating must occur, so no organisms can be made to mate with specific individuals. Number 3 is gene flow, meaning no organisms from an outside population can contribute, and no organisms in the population can leave. And then 4, right there, is next an infinite population size, meaning the population can be large and sustainable. And then 5 is that finally there is no natural selection that can occur, and individuals cannot pass on a gene due to environmental advantages. And so as long as those conditions are met, we have Hardy-Weinberg equilibrium can occur, and if not, then a population is not in Hardy-Weinberg equilibrium. And now that we understand the concept and its conditions, let's explore how you know if it's occurring.
We can use this equation to determine if evolution is occurring. To do this, we need 2 generations of the same population. After using the equation, we can explore the answers to see if they are similar or not. If the numbers obtained from both populations are the same, then evolution is not occurring and equilibrium is occurring. If we compare the results from the 2 populations and they are different, then the populations is not in equilibrium and the evolution is occurring. In scientific terms, the allele frequencies are the same.
Now, there are 2 parts to this equation. The first is p squared plus 2pq plus q squared equals 1. The second is p plus q equals 1. Now, what do these numbers mean? For the first equation, p squared is the number of individuals with a homozygous dominant genotype, meaning the 2 alleles for that gene are the same and represent a dominant gene. 2pq is the number of heterozygous individuals, meaning the 2 alleles for the specific gene are different, one dominant and one recessive. And p squared is the number of homozygous recessive individuals, meaning that the 2 alleles for that gene are the same and represented by the recessive gene. Now for the second equation, p plus q equals 1. P itself is equal to the frequency of the dominant allele, representing the frequency of the dominant allele as it appears in the population. Q is the same, but for the recessive allele. 2pq is multiplied by 2 in this instant because heterozygous can come about in 2 ways due to genetics. Now let's see this equation in action.
Let's say we have a population of 100 fish and 25 are red. If red is a recessive trait, find all of the variables in the equation. So 25 out of 100 is 0.25. This is equal to q squared. How do we know this? If q squared is the number of individuals with the recessive phenotype, then only homozygous recessive individuals can express it. And we know from Carson's explanation that homozygous recessive individuals is equal to q squared. So from here, it is basic algebra. The square root of 0.25 is equal to 0.5, or q. Now we know p plus q is equal to 1. So then p must also be 0.5, and p squared must be 0.25. We've now easily solved for 4 of the 5 variables. All that's left is 2pq. We know that p and q are both equal to 0.5, so 2 times 0.5 times 0.5 is equal to 0.5 as well. This gives us all the variables.
We can check this by plugging in all our variables back into the original equation, and it should all add up. But what does this mean? On their own, these numbers don't mean much, but if we were to reevaluate this population in a few generations, we could apply the same math. So let's say in our next population that we find p is equal to 0.7 and q is equal to 0.3. These create different frequencies and numbers. This means that evolution is acting on this population because the allele frequencies are changing. But if we end up getting the same numbers after reevaluating the population, evolution is not acting on the population.